The School of Applied Mathematical and Physical Sciences was established in 1999. With the establishment of the school, the National Technical University of Athens, NTUA, recognized that technology advances when basic sciences meet engineering. At the same time, NTUA responded to the growing demand of the R&D industry for engineers combining firm mathematical and physical science education with interdisciplinary collaboration skills. The school is branched into 4 departments: mathematics, physics, mechanics, and humanities and social sciences and law. The main aim of the undergraduate curriculum of the school is to provide sound education on basic sciences, as well as to offer knowledge specialization, which is required to solve complex problems appearing in all industrial and technological activities of the modern world economy. This target is achieved by providing firm fundamental knowledge of mathematics, physics, mechanics, engineering, information science, economics, and humanities during the first 4 semesters, where the curriculum is common for all students, and then through specialized advanced sciences and engineer-oriented courses during the last 6 semesters of studies. The graduates of the school are very successful in the professional arena, taking up competitive job positions in all sectors of the economy, compatible with their skills, whereas they are also very successful in the academic and research fields internationally. The school is the leading partner in 5 interdepartmental graduate programs of NTUA and partner in 13 more interdepartmental graduate programs of NTUA. The faculty of the school shows amazingly rich research and scientific activities funded by national and European grants.
I welcome you at the Laboratory of Optoelectronics, Lasers and Applications of the National Technical University of Athens. The research activities of the Laboratory of Optoelectronics, Lasers and Applications were started at the 1978 and were mainly the development of different laser systems based either on gas or solid-state materials. These lasers were lasers of carbon dioxide, nitrogen, and mainly ruby and ND-YAG lasers. The research applications of the lasers we developed here include the development of solid-state laser for spaceborne and ground-based activities, the environmental applications for air pollution monitoring, biophysical, biomedical, and also the cultural heritage, as well the fiber laser simulations. The environmental applications of lasers include the LiDAR technique, which is applied on the monitoring of air pollution and sea pollution. The air pollution monitoring is focused on the aerosol profiling using, as we said, the LiDAR technique, which gives us information about the vertical distribution of aerosols in the atmosphere from the Earth's ground up to altitudes of up to 20 kilometers height. We are part of European LiDAR network, which is spread all over Europe and gives information about the vertical distributions of aerosols and their optical and physical properties, as well as their chemical properties, which are then provided as input to climatic models to forecast the global change, which is attributed to aerosols and clouds. also part of the Actris project, which aims to monitor the air pollution of mostly the aerosols all over the European continent, which is part of the ESFRI research infrastructure of Europe.
I am Ioanna Zergioti. I'm professor in the School of Applied Mathematics and Physical Science of the National Technical University of Athens, and I am the head of the group of Materials and Laser Microprocessing. Our group is working on two applications. The first is the use of laser pulses for sintering and printing of metallic inks for flexible electronics. And the second application is the laser printing for biomedical applications. In the first lab, we have high power lasers and high rep rate, and we are able to print different kinds of materials like metallic materials or oxides or isolating materials for devices, for electronic devices or interconnects. In this laboratory, we're also working on the use of laser pulses for the transfer of 2D materials, two-dimensional materials like graphene, molybdenum sulfide, bismuth selenide for advanced electronic devices, high mobility transistors and other applications. In this laboratory, we are working on a big consortium with European partners for the development of the process as a high-speed complementary approach for the printing of organic photovoltaics and touch sensors. In this laboratory, we are mainly focused on the printing of chemical compounds and of biological compounds. In both applications, we are collaborating with the Bioacademy of Athens, and more specifically, we have two projects. The first one is for the printing of pharmaceutical compounds, and the second one is for the printing of cells for regenerative medicine applications. Our future plans are related to the translation of the research out of the lab to succeed on developing reliable products and to have a further development of our research in real products. So we are very much keen to see our research to exit from our university labs.
The Financial Engineering and Mathematical Optimization Laboratory, FEMOLab, was founded in 2016 and is a certified research unit of the School of Applied Mathematical and Physical Sciences of the National Technical University of Athens. My name is Antonis Papapantoleon. I am an assistant professor of mathematics and the current director of FEMOLab. Lab specializes in the modeling, quantification and optimizations of processes arising in financial and energy markets and more generally in economics and finance. Many systems and processes we are modeling are governed by randomness. Think for example of the prices of a stock traded in the exchange or the amount of energy produced by a wind turbine. The way we can attack a question or problem can be roughly separated in 4 steps. In the first step, we analyze the data of the problem using tools from statistics and data sciences in order to understand what are the key features that should be modeled. In the second step, we design a model or system of equations for the problem at hand using tools mainly from probability and stochastic analysis. In the third step, we simulate a model or solve the system of equations using tools from numerical analysis and operations research and study the properties of the simulation or solution. In the final step, we code the solution in a computer and provide the algorithm to a possible end user. Mathematical theory supports the modeling phase as well as the experimental results and computer-aided simulations by explaining why to choose one model or what range of parameters a numerical method works or fails. Uncertainty quantification is an important aspect of our work. It allows us to provide detailed information about where the system may lie in the future and quantify this in many ways, for example by providing the distribution of possible outcomes, confidence intervals, and quantiles related to worst-case scenario outcomes. These are crucial information for risk management purposes across various industries. A possible contribution to society is the development of risk management tools that would amplify the effects of a future crisis. The research carried out at FEMO-Lab is supported by national and international funding agencies such as the Hellenic Foundation for Research and Innovation, the Europlace Institute of Finance, and the Horizon 2020 program of the European Union, as well as by industrial projects. FEMO-Lab has the know-how to analyze and model systems and processes related to random phenomena, to provide solutions and to quantify their properties, and to validate their compliance with various regulatory frameworks.